So in the last class, we finished with star delta transformation. We also did some numericals. We'll continue with some numericals before we proceed to unit number 2. So I'll be taking some select problems from Fundamentals of Electrical Circuits by Alexander Sedico, and will not be there are a number of problems given, unsolved problems that are given at the towards the end of unit 2. You can check them out. You should actually try and solve as many as you can. Fine. So let me take problem number 2.17. So this is actually fifth edition of the book that I am having, that I'm using. So the problem numbers may vary depending upon which edition you are using. So problem number 2.17, we have here a circuit. So in this problem, we have to solve for the values of V1, V2, and V3. We do not have the values of resistance, so we'll just be obtaining the equations of V1 and V2 and V3 from the input voltage that are available to us. Some of them we can, let's see actually what we'll be able to obtain. Fine. So looking at this circuit, we can directly say from this circuit at least, uh, we can directly say that since V3, across V3, the voltage applied is 10 volts. So V3 will be equal to 10 volts. Fine. So this is one thing that we have been able to obtain. Now let this be loop 1, this be loop 2, this is loop 3. So by applying KVL to loop 3, we have obtained V3 is equal to 10 volts. Now let's apply KVL to loop 1. By applying KVL to loop 1, we have 24 volts minus, if current is traveling in this direction, 24 volts is in polarity opposed to that of V1, so it will actually be minus. So 24 minus V1 Polarity of V2 and 24 volts is same, so V2 will be added in this equation. 24 minus V1 plus V2 is equal to 0. So from here we have V1 minus V2 is equal to 24. So this is equation number 2. Applying KVL to loop 2. Uh, Current is moving in this direction. We can write this as V3 plus 12 plus V2 is equal to 0, which implies V2 plus V3 is equal to minus 12. But so this is one equation, this is our third equation. From substituting equation number 1, in equation number 3, we get V2 plus 10 is equal to minus 12, or we can say that V2 is equal to minus 22 volts. So this is equation number 4. Substituting in equation number 2, V1 minus minus 22 is equal to 24, which implies V1 plus 22 is equal to 24, which implies V1 is equal to 24 minus 2, that is V1 is equal to 2 volts. So we have seen here how we can obtain actually the values of V1, V2 and V3 in this circuit by applying simple KVL equation. Moving on, I'm taking now problem number 2.21. So you have a 1 ohm resistor here, you have a 2 ohm resistor here, you have a 5 ohm resistor here. The voltage across this is Vx. This is a dependable voltage source whose value is equal to 2 Vx, and this is a 15 volt DC voltage source. So our aim is to find Vx in this case. We have to actually obtain Vx in this particular case. So if current I is flowing in the circuit, by applying KVL, we can say that 15 is equal to 1. So when current flows in the circuit, this becomes plus minus. This is already plus minus. This becomes plus minus like this. Fine. So it is actually flowing in this direction. So you can either write 15 minus I, or you can say simply 15. This 15 volts is equal to I into first resistance, that is 1 ohm, plus 2Vx. Fine. 2Vx has the same polarity as this particular resistance. So it will be added to this particular voltage here. So it's also a drop here, plus 2Vx Fine. So I is flowing through this resistance also. I into 5 plus I into 2. Fine. So 15 is equal to 2Vx plus 5I plus 1I plus 2I. So this becomes equal to 8I. So this is equation number 1. But from this circuit, Vx is equal to what? It is the voltage across this 5 ohm resistor. So that's simply equal to 5 into the current flowing through that resistance, that is I. So but Vx is equal to 5I. So substituting 2 in equation number 1, we get 15 is equal to 2 into 5I plus 8I, which implies 15 is equal to 10 plus 8I, that is 18I, which implies I is equal to 15 by 18, or you can say 5 by 6 amperes. So if I is equal to 5 by 6 amperes, substituting this in equation number 2, substituting equation 3, in equation number 2, Vx is equal to 5 into 5 by 6, that is 25 by 6 volts. So this was our problem number 21. Let us take problem number 2.22. In problem number 2.22, we have the circuit. So this here is a dependable current source, and it is dependent, since its value is equal to 2 V naught, that means it's dependent upon some voltage. We have a 25 ampere current source here. We have a resistance of 10 ohms here. You have again a resistance of 10 ohms here. There is a voltage V naught across this, that is having the polarity plus V naught. Fine. So you have to obtain the value of V naught here, as well as V naught. You have to obtain V naught, and you have to obtain power absorbed by the dependent source, PDS, that is power absorbed by the dependent source. Fine. This is problem number 2.22. So a 25 ampere current is flowing from here. A 2V naught current is flowing from here. So the total amount of current that's actually going here is 25 plus 2V naught. So what is the value of, so let this be equal to I. Fine. So I we know is equal to 25 plus 2V naught. I is also the current that is flowing through this 10 ohm resistor. So if I is the current flowing through this 10 ohm resistor and the voltage across this 10 ohm resistor is V naught, that means V naught is equal to I into 10, or which implies V naught uh, I is equal to V naught divided by 10. So this is equation 1, this is equation 2, substituting 2 in 1. So once you substitute equation number 2 in equation number 1, you get V naught by 10 is equal to 25 plus 2V naught, which implies V naught by 10 minus 2V naught is equal to 25, which implies V naught minus 20V naught by 10 is equal to 25, or minus 19 by 10 V naught equal to 25, which implies V naught is equal to 25 into 10 divided by 19 minus 250 by 19 volts. So this is the value of V naught here. So we have obtained the value of V naught minus 250 by 19. 1 minute. So if we divide 250 by 19, two fifty by 19 is 13.15 ampere. This is equal to minus 13.15 volts. So we have obtained one part of this problem, that is value of V naught. We need to now obtain the power that's actually absorbed by the dependent source. To obtain that, this is our circuit, or you can also say this is our circuit. We have a 20 ohm resistor here. I have combined the two resistances. We have a current source here. We have a dependent current source here. This is 25. This is 2V naught. Fine. Uh, so voltage across this, let it be equal to capital V. So power absorbed, the current that's actually flowing through this path is 2V naught. Current through this path is 2V naught. Voltage, since all these three branches are in parallel, voltage across this will also be equal to V. So power absorbed will be equal to, power absorbed by this dependent current source will be equal to current into voltage. Current is 2V naught into capital V. So this is our power equation. So we have seen that power will be equal to 2V naught into V, where V is equal to what? Where V is the voltage across this 10 ohm resistor, which will be equal to I into R, that is I is capital I that we have used earlier here, fine, and R is here 20 ohms, the total resistance across this path, which implies V is equal to 20 into I is what? I is V naught by 10 from equation number 2, fine. So this is capital V is equal to 2V naught. So capital V is equal to 2 V naught. We are getting this value of V. So substituting it here, P is equal to 2 V naught into 2 V naught, that is equal to 4 V naught square, where 4 into V naught is minus 13.15 square, which is equal to, let me calculate this, 4 into 13.15 into 13.15, that is 691.69. So this is the amount of power absorbed by the dependable current source. So let's move on. So we have problem number 2.24 now. We have a circuit like this. We have a dependable current source here. You have a resistance R3, you have a resistance R4. So there is no connection here. Fine, there is no connection here. So this is equal to alpha I naught. The value of this voltage source is Vs, and the current I naught is flowing from here. And V naught is the voltage. So this is in the question. Now for this circuit, find V naught by Vs. We have to find V naught by Vs in terms of R1, R2, R3, R4, and alpha. And first we have to obtain this. Then the second part of this question is, if R1 is equal to R2 is equal to R3 is equal to R4, what value of alpha will produce V1 by Vs is equal to 10. Fine. First of all, let us find out V naught by Vs in this particular circuit. Uh, so let this be loop 1, this be loop 2, this be loop number 3. Applying KVL to loop 1, Vs is equal to I naught into R1 plus I naught into R2. Right? So this is one equation that we are obtaining, that is Venus. I naught R1 plus I naught R2, or we can say Vs is equal to I naught R1 plus R2. We have to find the value of V naught Vs in terms of alpha, R1, R2, R3, R4. So I naught and V naught cannot be in that equation. So let this be equation number 1 for now. Applying KVL to loop number 2. To loop number 3 rather. V naught is our output voltage. Let the value of uh, R3 and R4 are in parallel. R3 and R4 are in parallel. So V naught is the voltage across R3 as well. We do not need to apply KVL for that. V naught is the voltage across R3 as well. Alpha I naught is the current that's actually coming from this path. Fine. So if current I1 is flowing here, I2 is flowing here, we can either try to find out I1 or I2. Let us say we are finding out current I2. I2 will simply be the current that's actually coming into the circuit, that's total current alpha I naught by current divider law into the value of opposite resistance, that is R3 divided by R3 plus R4. Fine. Where I2 is what? I2 is current flowing through R4, which can also be written as V naught divided by R4. Rather minus V naught divided by R4, because of the polarity that has been fixed in the question, this being plus and this being minus, I2 will be equal to minus V naught by I4. Right? So minus V naught by I4 is equal to I naught into R3 divided by R3 plus R4, which implies minus V naught, rather plus V naught, is equal to minus alpha I naught into R3 R4 divided by R3 plus R4. So this is V naught. This is equation number 2. Dividing equation number 2 by equation number 1. V naught divided by Vs is equal to minus alpha I naught R3 R4 by R3 plus R4 divided by I naught R1 plus R2. I naught and I naught cancels out, so this is equal to minus alpha R3 R4 divided by R1 plus R2 R3 plus R4. So this is the value of V naught by Vs that we are obtaining. And the second part of this question is, if R1 is equal to R2 is equal to R3 is equal to R4 is equal to, it does not have any value, these are all equals, what will be the value of alpha for V naught by Vs equal to 10? Mod of V naught by Vs equal to 10. Why? So mod of V naught by Vs, so minus sign will cancel out, and R2, R3, R4, they are all equal. So let that be equal to capital R here. So this is equal to alpha naught into R3 R into R divided by R plus R into R plus R, which is equal to alpha naught into R square by 2R into 2R, that is 4R square. So 4R square becomes R square and R square cancels out. So this becomes equal to alpha naught is equal to 1 by 4, which implies V naught by Vs, which is actually equal to 10 is equal to alpha. This was only alpha here. I don't know. I'm writing alpha or not. Alpha divided by 4, which implies alpha is equal to 40. Alpha has to be equal to 40 for this equation to be true. Similar to this question, we have problem number 2.25. We have a 5 milliampere current source connected across a 10k resistance. This means actually 10 kilo ohm resistance. We simply write it as 10k, across which the voltage has been given is equal to V naught, and there is a dependable current source here whose value is 0.01 V naught. It is connected across a 5k resistor, which is connected in parallel with a 20k resistor. So we have been asked to find current, voltage, and power associated with the resistor, with the 20k resistor. Fine. So we need to find out V. I'm writing this as V across this. We need to find current I across this, and we also need to find power, that will be simply equal to V into I across this. So now to solve this problem, so 5 milliamperes is flowing across this. That means V naught is equal to 10k, that means 10 into 10 is power 3 ohms, into current, that is 5 milliamperes, that is 5 into 10 is power minus 3. Fine. So 10 in this and this cancels out, which implies V naught is equal to 50 volts. Fine. So we actually obtain the value of V naught. Now we know this current source is equal to 0.01 V naught. That means since V naught is equal to 5 volts, so this current source here, let this current be I1, this be V1. Therefore, power is equal to V1, V1 current from this path is I2. Let this current be equal to I. So current I, capital I, is equal to 0.01 into V naught, that is 50 volts. So this is 50 divided by 100, that is 0.5 amperes. Fine. So point I is equal to 0.5 amperes. So I1, we have to find I1 by current divider law, will be equal to I, that is into the opposite resistance, that is 5 kilo ohms, divided by the total resistance, that is 5k plus 20k, which implies I1 is equal to I, that is 0.5 into 5k, that means 5000, divided by 5000 plus 20,000, which implies I1 is equal to 5,000 by 25,000 is 1 by 5, so this is zero point 0.5 divided by 5, which means 0.1 amperes. Fine. So I1 is equal to 0.1 amperes. So if I1 is equal to 0.1 amperes, V1, that is the voltage across this, will be equal to I1 into R. I1 is 0.1 into R is 20,000. So this is equal to 2000 volts. So power will therefore be equal to V into I, that is 2000 into 0.1, that is 200 watts. So this is question number 2.25. Let us do problem number 2.238. So problem number 2.38, we have the circuit. We have 35 volts, 2.5 amperes. We have a 15 ohm resistor here. We have a 6 ohm resistor here. We have a 20 ohm resistor here. You have 12 ohm resistor here. This is 6. This is 12. And there is an 80 ohm resistor here. This branch is connected. And there is also a 60 ohm resistor across this path. So this total is R equivalent. Current is I naught. So the question is, you have to find R equivalent. You have to find I naught. Right? So we have this particular diagram, and you have to actually solve for R. The major problem here is actually for solving for R equivalent. If you know, if you can solve for R equivalent, you can find the value of I naught easily. So how to approach this? So if there were a resistance here, then this problem would have been a little bit tough to solve. We would have to go for star delta transformation. Since there is no resistance here, this point, this node and this node, they are almost same. So you can actually say this circuit is connected like this. So you can actually ignore this particular portion of the circuit. So it becomes as good as this thing. Fine. So now you have 20 and 80. They are in uh, parallel. You have 6 and 12. They are in parallel. So this circuit becomes 35 volts, 2.5 amperes. Then you have 15 ohms here. You have 6 and 12. They are in parallel. So 6 parallel 6 into 12 divided by 18. That's 72 by 18. You have a 60 ohm resistor still from this side. 20 and 80 they are in parallel, so that's 1600 divided by 100, that is 1600 divided by 20 plus 80, that is 100. So this is 16 simply. 72 by 18 is equal to 4 actually, so I can simply write this is 4. Fine, so this is your circuit now. 4 and 16 they are in series. 4 and 16 in series means they become 20 volts, and this 60 is now 20 ohms, sorry, this 60 is connected here. So 15, 20 and 60 they are in parallel now, so you can find out the value of R equivalent, then you can find out the value of I naught. So that is the, so you have a number of problems that you can actually do. So these were some important ones which I thought might be of use to you. Fine. So rest of the problems they are based around these basic problems that we have covered today. So we'll end the lecture with that today.